Welcome back, welcome back, welcome back. I'm Miss Lisa. This is my YouTube channel where we learn about things that are math and science. Today we're learning about physics, and in particular we're learning problems that have to do with impulse and momentum. This is a class primarily designed for homeschoolers where we're going through this physics book that you can see behind my calculator. But anybody who likes the way I explain things, come on in. You are welcome to be here. Like, share, and subscribe. I'm trying to get 1,000 subscribers so that I can do YouTube Live. They won't let me do it till I have 1,000 subscribers, but I got an extra one yesterday. So, you know, we're getting there, slow but sure, we're getting there. Maybe it'll happen. All right. So this is the math part. So if you didn't watch the first video, you might want to go watch it first. But if not, plunge on in. Let's talk about momentum. I use a TI-84 graphing calculator, so I recommend you do too. It's a great calculator. And last time I told you about that there's an app that really helps with these vector problems. So see that little pink button that says apps? So you turn it on here, you push apps, and see that one that says SciTools, Science Tools? You go down to it or push 7. And it is a Texas Instrument program. That means it wasn't written by like a professor or something. It's one at Texas Instrument that you can get. If you don't have it, you can download it from their website. So I'm going to push any key. And the one that works with this that you want, there's also something that's a sig fig calculator. But there's one that's number 4. A vector calculator. So this one, you pick your vectors and you can put them in there, and then you can add them and subtract them and things like that. So we want to quit out of this. I think I'm just going to actually turn it off because it's not too easy to quit out of. Let's see if it's gone. Yes, it's gone. All right. That's the easiest way to get out of that one. Some of them have like where you use these keys and exit, but that one at that point didn't have the exit, so I just quit out of it. All right. So now we're on our regular math screen. We can make it look better by clearing out. And what we're going to start with is our first example momentum problem. And if you want to use that SciTool program, there's probably videos, since it is a Texas Instrument program, there's probably videos on YouTube you can find where someone's showing you how to do it. I've made a video for it, but it's on Facebook. And with privacy, you probably can't get to it. So maybe eventually I'll make another one, or I might have my kid make a video for it. But right now, we're going on and doing it the old-fashioned way without that program. But we're not going to be using it on this one. It's the last problem. Okay, so example problem number 1 is on page 177, and this is what it says. You can read silently while I read out loud, or you can read out loud because I can't hear you. A baseball, and remember, these are word problems, and what we want to do is get rid of the words and just make it numbers because then it's easy. A baseball of mass 0.14 kilograms. So that's my first number. I come over here and start listing it in my knowns and unknown list. Okay, and so that's a mass. So I put M for that. Is moving at 35 meters per second. Well, I recognize meters per second is a velocity, so I put 35 meters per second. And it's a positive one. I usually don't bother writing if it's positive, which means just it just means that it's in a certain direction, and then we might look at how that direction changes. Find the momentum of the baseball. So that's my first one. Momentum is P, and so I write, now I've got my knowns and unknowns, and now I put the formula. Is there a formula that relates mass, velocity, and momentum? Why, yes, there is. Momentum equals mass times velocity. So now I substitute, and I put right underneath the M, I put what mass is. Right underneath V, I put what the velocity is, and I multiply it, and it's 4.9 meters per second. You can see it is the momentum. So we check our answer. I didn't have the whole thing. I left off the kilograms. Kilograms time meters per second. I was like, that's not right. We'll shove a little kilogram in there. Now there's a kilogram. All right. So always watch your units. Do better than I did. So it's positive 4.9 kilograms times meters per second. Okay, so the next part of the problem says, and I usually like to solve one part before I even read the next part because it just gets overwhelming and confusing. B, find the velocity. So my new thing is, what's the velocity? Okay. B, find the velocity at which a bowling ball with a mass of 7.26 kilograms, so next I write down mass, 7.26, would have the same momentum as the baseball. So I get my baseball momentum and I go over here and write it. Now I have my knowns and unknowns, and I think, is there a formula that relates mass, momentum, and velocity? Yes, there is, the same one. I write it down and sing substitute. And underneath P, I write 4.9. Underneath M, I write 7.26. And I keep V the same to be my unknown. Now, why is V not alone? It's being multiplied by 7.26. So I do the opposite. I divide both sides by 7.26. These cancel out, and I have 4.9 divided by 7.26, and it is 0.67. So we'll go ahead and do that on the calculator. So we've got 4.9 divided by 7.26, and there it is. Notice that this baseball, even with the same momentum, because it has a much bigger mass, is going much slower, 0.67, as opposed to the other one was going 35 meters per second. So mass has a huge impact on momentum. And you already kind of know that. All right, next problem. Now we're going to talk about baseball again. It wasn't about baseball before. All right, so we're going to get rid of the words and make it, and just make it numbers so it's easy. A 0.144 kilogram baseball, so that's my first thing. I have a mass of 0.144 kilogram baseball, is pitched horizontally at 35 meters per second. That's a velocity. So I wrote that down, 38. I think it said 35. 38 meters per second. So that's my initial velocity here. Okay. After it's hit by a bat, it moves horizontally at negative 38 meters per second. So it's going one way, you hit it, and it goes the other way. That's why it's negative. It's just showing that it's going in the opposite direction. Okay. So my first question is, what impulse did the bat deliver to the ball? Okay. So there's my negative 38 meters per second. And what I want is impulse. And impulse is change in momentum, delta P. That's what I don't know. So I think, is there a formula that relates these? And it's this, that the change in momentum is the final momentum minus the initial momentum. And momentum is mass times velocity. So I can calculate these for both of them with the thing I don't know and get the change. The change is what I don't know. So my mass is 0.144 times my final momentum. My final speed is negative 38 minus my, there's the minus the mass. It's the same mass. The baseball didn't change mass. Minus the mass times the initial speed, which was 38. Put that all in your calculator, and it's negative 10.944, which then the book rounds off to the change in momentum is negative 11. And so we go check our answer, and yay, we got it right. Go us. Do y'all want me to put that in the calculator? I can do that. Let me show you how I put that in the calculator. I use the parentheses just like they do. So I'm going to type it in just like that. Beginning parentheses, and the parentheses are right here. Beginning parentheses, 0.144 times negative, and the negative is down here, negative 38, in parentheses, minuses are over here, minuses go in the middle here, beginning parentheses, 0.144 times 38. So I've typed it in exactly. I get my in parentheses, hit enter, and oh, I left off my 1. I was like, and I got the wrong answer. Let's see if it'll let me arrow up and fix it. Nope, I don't think so. I'd have to retype it. Do I have to retype it for you? Sure, why not? Okay. That's what I get. It's hard to do it looking through the camera at it and looking back and forth. And that's probably why I have terrible camera work. Y'all are like, oh, she's making me sick. My physics teacher is making me sick. Times 38 in parentheses. Let's try again. There's the right answer. Ta-da! Yay. Always cheer for yourself when you get it right. You're being clever. All right. B says, if the bat and ball were in contact for 0.8 milliseconds, what was the average force the bat exerted on the ball? Okay. Notice that these are milliseconds and our other things are seconds. So this is for B. We know the change in momentum. We know the impulse is -11. We got that in the last problem. We know the time is 0.8 milliseconds, but because that's seconds and that's milliseconds, we need to make sure they have the same units. So we're going to convert that to seconds, and we're going to use our little trick. King Henry's daughter bakes delicious chocolate muffins. We're going from milliseconds to the basic unit of seconds, so we count how many frog jumps it is. 1, 2, 3. So we move our decimal point 1, 2, 3 places, augmenting zeros. 1, 2, 3, and that's how many seconds it is. Okay? And then it asks us, what was the average force? So our formula that we have for this that relates momentum, time, and force is this one. That the impulse, the change in momentum, is the force times the change in time. So our momentum is, our impulse is -11. Force is what we're trying to solve for, and our change in time was 0.0008. Why is force not alone? It's being multiplied by 0.0008. So we do the opposite. We divide both sides by 0.008. The 0.008s over here cancel out, and you get this. And your book rounded it off and put it in scientific notation. But that's what you get on your calculator. So don't be confused by that. All right. C. Find the average acceleration of the ball during contact with the bat. So for C, where did I do it? A, B, C. Okay, I did it over here. All right, so what we need is acceleration. And this is our formula for acceleration. F equals ma. I call that one our famous formula. People say it's the most famous formula in physics. So there it is, F equals ma. I really think E equals mc squared is more famous, but don't let that confuse you. This is the famous formula. That's what people call it. And it looks like maybe so we got some fame things in there. All right, so our force we just got from our last problem. Our mass stays the same. We're solving for acceleration. That's an A, not a 9. Acceleration is being multiplied by 0.144. So we divide both sides by 0.144, and we get this, which your book rounds off to 10,000. All right? So that was pretty fun, wasn't it? So be sure to stop this and try it on your own calculator. All right, problem number 3. Woohoo! Okay, a glider of mass 0.355, so we first start by listing our knowns and unknowns, moves along a frictionless air track with a velocity of 0.095. It collides with glider B with a mass of 0.710, these are kilograms, moving in the same direction at a speed of 0.045 meters per second. After collision, glider A continues in the same direction with a velocity, so glider A's velocity now is 0.035 meters per second. What is the velocity of glider B after collision? So look, we got rid of all those words and got just that nice little stream of numbers. Isn't that better? Okay. And now we think about, and remember that momentum is mass times velocity. So, and we also know that the two momentums before collision is equal to the two momentums after collision. So our big formula is momentum A plus momentum B equals, after the collision, momentum A plus momentum V. And we call this momentum A prime, B prime. Okay, so for each of these momentums, we're going to substitute mass and speed. So mass A times speed A, mass B times speed B before collision, mass A, speed after the collision, B after the collision. So we know the mass of A is 0.355. We know the velocity of A before the collision is 0.95. We know the mass of B is 0.71. And we know the velocity of B before the collision. On the other side, we know the mass of A after the collision, it's the same. We know the velocity of A after the collision. We know the mass of B after the collision, it hasn't changed. And what we're looking for is the velocity of B after the collision. And we're going to solve for X, and I did it all on my calculator. So I want to show you how I did it all on my calculator, okay? So I'm going to clear out what's in here so you can see it really good. And I'm going to start with putting in exactly how it's written, the left side of the equation. I'm going to put all of that in, just how it's written. So I'm going to do beginning parentheses, 0.355 in parentheses, beginning parentheses. Your calculator knows that parentheses is times. Beginning parentheses, 0.095 in parentheses, plus beginning parentheses 0.71 in parentheses, beginning parentheses 0.045 in parentheses equals. Okay, so that's my answer for this side. Now I'm trying to get this alone. It's being added to this. So the opposite is subtract. What I do to one side, I do to the other. So I need to subtract this from my answer to get that alone. So I'm going to say minus, and that puts answer minus. It copied that there. And now I'm going to put it in parentheses that I want it to multiply these together. So I'm going to put an extra parentheses because I want this whole term to be in parentheses subtracted from that. But now I want to use parentheses to do this math. So I'm going to do 0.355 in parentheses, beginning parentheses, 0.035 in parentheses, and now I have to close it, so I do another parentheses, okay? So now that's going to subtract that term around to the other side, and I get another answer. So now I've got on this side, what I have left is 0.71 times x. So to get rid of it, I do the opposite. It's being multiplied, so I divide both sides by this. So I want my answer divided by, I just hit divide and it puts it up there, 0.71. And the answer is 0.75, and the answer is 0.75. Now, if you don't want to do that, you can do it more step by step. But it's just a pain having to write down all of those numbers. And I wanted to show you that it could be all done. Keep all the numbers as much as possible. And then at the end, think of significant figures. You can also use alpha y for fractions. Remember, we have this shortcut menu where you can go alpha y equals, select number 1, and it gives you the little boxes for fractions. So like I could do 2, go down, put 3, and I've put in 2/3. And now it told this to me as a fraction. If I wanted it to tell it to me as a decimal, I go to math, which I call the ironic button, because aren't they all math? And it says, choice number 2 is put your answer in a decimal. Choice 1 is put your answer in a fraction. So if you have a decimal and you need a fraction, very useful for algebra because they always want it in a fraction, use button 1. If you need your answer in a decimal, very useful for physics because they always want it in a decimal, go down to number 2 and it says put your answer in a decimal, and there it is. All right, so those are just some little calculator tricks that are useful. Okay, let's go moving right along. Those are the girls pushing each other that I talked about. All right, so example problem number 4. Okay, I'll read it out loud. You read it to yourself. Wait, I need some water. Okay, an astronaut at rest in space. Okay, so we know that his first momentum is 0. Fires a thruster that expels 35 grams of hot gas at 8.75 meters per second. So the mass of my astronaut is 84. The mass of the gas is 35. Notice that this is in kilograms and this is in grams, so I have to use King Henry's Daughter Bakes Delicious Chocolate Muffins, and I want to go from grams, the basic unit, to kilograms. I'm going to put it in the same one as the astronaut. So I move it 1, 2, 3 places that way. So my decimal goes 1, 2, 3 places that way, 1, 2, 3, and it's 0.035 kilograms. Okay, both of them, their initial speeds are 0. The speed of the velocity of the astronaut after firing is what we don't know. That's our question. But we do know the speed of the gas after firing, and it's 875 meters per second. So now we've got all of those words are gone, and we just have these knowns and unknowns. Isn't that better? Okay, so now we think, is there a formula about this? And yes, there is. That momentum before equals momentum after. Our momentum befores were 0 are going to equal our momentums after. So I went ahead down here. So my formula is momentum is mass times velocity. So I went ahead and showed you why those were zeros, just in case you didn't understand that we have MAVA plus MBVB equals the mass of A times the velocity of A prime after firing, mass of B, speed of B prime after firing. So my astronaut times the speed, and anything times 0 is 0. My gas times its speed, anything times 0 is 0. 0 plus 0 is 0. On this side, I have the mass of the astronaut times his final speed, and plus the mass of the gas times its final speed. So I don't know why I wrote 625 there. Let's make sure I did it right. I'm a little dyslexic, and sometimes I just write numbers at random that don't make any sense. Because that should be 875. Oh, I get it. I was looking at that and not paying attention. If you multiply these things together, it's that. I made too big of a gap. So the first thing I did is I multiplied 0.035 times 875, and it's 30.625. Okay, so then I subtract, because these are added and I'm trying to get this alone, I subtract 30.625 from both sides, and it ends up over here. Now I've got 84 over here next to VA. I want VA by itself. It's being multiplied by 84, so I divide both sides by VA, and I get 0.3645. And this is negative. We can put negative and a 0 there. And your book rounds it off to negative 0.36. And what that negative means is that they go in opposite directions. The gas goes one way, the astronaut goes the other way. So that's pretty fun. Put it in your calculator and give it a try. Okay, so the next thing we're going to talk about is this. What about when things go off at angles? And when we get angles, what do? Vectors. That's right. So here is our example problem. You have a ball coming along. It hits this ball. This ball goes off this way. That ball goes off that way. Both balls are 2 pounds. This ball is coming in with a speed of 5 meters per second. Okay, so step 1 says, well, let's read the problem first. A 2 kilogram ball, so mass A is 2 kilogram, is moving with a velocity of 5 meters per second. Sorry about that, I was wandering off. 5 meters per second. It collides with the stationary ball, so ball 2's speed is 0. Also with a mass of 2. Ball 2's mass is 2. After the collision, ball A moves off with a direction of 30 degrees. So theta A, I said, was 30. To the left of the original ball, ball B moves off in a direction of 90 degrees. So theta B is 90. And then this we can think of as a triangle. So my third angle is 60 because the three angles have to add up to be 180 of a triangle. It's a rule about triangles. The three angles have to be 180 that you probably learned in geometry. All right, so that's what we know. So A says draw a vector diagram to find the momentum of ball A and B after the collision. So my first A, when it's coming along, its momentum, remember, where did I write it down? Well, anyway, momentum equals mass times speed. So my mass is 2, my speed is 5, so my momentum of this ball coming in is 10, all right? Now, so here's my angle 30 that this ball is now going to go off at. And this ball is going at 90 degrees. So I take my thing and I move it down because you have to add vectors head to tail. So I move it down and put it there. And then my resultant is going to be right there, the other side of my triangle. Okay. So I now have this 30, 60, 90 triangle. I know that my original thing coming down here is 10, and I want to find out what these other two are. That's the next part of the problem. So I have the angles, and I can use this angle of 30, and I can use my trig functions to solve these two. All right? So here, this one we'll do first. This line is adjacent, and I know the hypotenuse, I know it's 10, and so I can use cosine, caught another horse. So the cosine of theta is adjacent over hypotenuse, caught another horse. My theta is 30, my hypotenuse is 10. I multiply both sides by 10 to get it out of the denominator, so I end up with 10 cosine 30, and I do it on my calculator. So on my calculator, I do 10 cosine 30, close it up, and there's the answer, 8.6. And I did it right. Yay! They rounded it off to 8.7. Now, what if you just did it with me and you got the wrong answer? You need to go to mode and make sure degree is lit up here and not radian. If you get wrong answers on these, you got to check your mode. All right, so now I want to get out of that screen. So I do second mode, which is quit, a very useful button. And now I want to get the opposite, some old horse. So I'm going to use sine of theta equals opposite over hypotenuse, some old horse. And my hypotenuse is 10, my theta is 30. So where did I write it? I don't think I wrote it again. Let's write it again down here. The sine of theta equals some old horse. So it's sine of 30 equals, the opposite is what I'm looking for. I'm going to turn it into an x because it looks like a 0. The hypotenuse is still 10. I multiply both sides by 10. So it's 10 sine 30 will give me the opposite. So 10 sine 30 is 5. So my opposite equals 5. And I check it up here, and da-da, and I got it right. Oh, there I wrote it, 10 sine 35. And I wrote it there. I kind of had it there for you. All right, part C. Now use the definition of momentum, P equals mv, so I wrote that down first, to find the magnitude of the velocities, okay? So my original momentum for ball A, we found, well, the momentum I just solved for ball A that's going off this way is 8.7. The momentum that I just solved for ball B is 5. They're both still 2. They didn't lose any mass. So if I want to figure out the new speed for ball A, I put in 8.7 equals 2 times the speed, To get speed by itself, I divide both sides by 2. These cancel out, and I get 4.35. In the book, rounded it to 4.4 meters per second. For ball B, the momentum I solved for is 5. Its mass is still 2. Divide both sides by 2, and 2.5 equals this speed in meters per second, the velocity. It doesn't have a direct, well, I guess it does have a direction. It is a velocity. All right, that's it. That's the end of the chapter. So do your homework. Remember, I give you the problems with that are the practice problems. They have the answers in the back of the book. Do them, enjoy it, have fun, and math is great. Science is great. Physics is great. Like, share, subscribe. I'm Miss Lisa, and I'll see you next time.